My apology, Dr. Nisa. I think that you have mute your mic. Please unmute your mic. Thank you.
Sorry. Okay, Assalamualaikum and good morning, ladies and gentlemen. Welcome to this insightful sharing session titled Developing Visual Analytics Tools for Insights Discovery, a case study of stay plot. So this event is proudly organized by DASCA, UITM Negeri Sembilan branch, a special interest group dedicated to activities in data science and predictive analytics. And we are delighted to have with us today a distinguished speaker, Associate Prof. Dr. Babanjida Ibrahim Babura from the Department of Mathematics, Faculty of Science at the Federal University Dutse International University, Jigawa State, Nigeria. Dr. Babanjida's extensive expertise and research interests span across exploratory data analysis, extreme event modeling, reliability analysis, computational statistics, robust statistics, and data science. So in today's station, Dr. Baba will share his expertise on visual analytics tools, focusing on the step plot as a case study. This session aims to provide valuable insights into how these tools can be developed and utilized to enhance data exploration and insight discovery, crucial for making informed decisions. Before we begin our online sharing session, please note that it will be recorded. Kindly ensure your microphone is muted. If you have any question, feel free to ask in the chat box. So without further ado, please join us in welcoming Associate Prof. Dr. Babanjida Ibrahim Babura. Thank you.
Thank you. A very good morning.
Yeah, welcome.
Welcome everyone for. Is even there, right? We have.
In Malaysia,
I'm
it's
speaking from.
2:30 p.m.
Yeah. So it's already afternoon.
Yeah.
Okay. Thank you. So thank you, Daska in general, and Dr. Nurul for inviting me for this talk. I don't know. I share with you. I'm using my mobile device because I had challenge with my computer. So I don't know whether you can share from there the screen. I mean the slides. I send you the slide, so I don't know whether you can share the slide from that end. Can you hear me?
Yes, sure.
Can you hear me?
Yeah. I will share the slide.
Okay. So bear with us, please. Been trying to. Okay, thank you. My talk today is developing visual analytics tools for insight discovery, a case study of star box plot. Okay, so this talk is going to focus specifically on developing the visual analytic tools. And when we say visual analytic tools, the tools are very, people used to be very conversant with those tools, especially the box plots. It's one of the basic tools that is very popular. And, it's popular in the sense that it is simple to construct, very easy um, to get insight from. And that is all what data visualization is all about. So in this data science age, when we say visual analytics is a very diverse area. Can you move to the next slide, please? Okay. When no, go back. Let me discuss the outline. The outline of my talk is visual analytics in general, then the exploratory data analysis, how they relate with the visual analytics, then our case study, because our case study is basically on the exploratory data analysis. So move to the next slide, please. So let's just look at the visual basic background behind the visual analytics. If we look on the early beginning, this visual analytics originated from information visualization and data mining in data mining fields. And actually, when you relate to exploratory data analysis, you will see it is far, far beyond that. So technological advances, which grows with advancement in computing power and the graphical capabilities, make people to embrace this approach in discussing data in general. So also the modern development, integration with AI, when we talk of AI these days, is trying to take over so many other things. So move to the next slide, please. Okay. So what are the benefits of the visual analytics? I think everyone joining this discussion must have some insight into the benefits. So, for example, enhanced decision making. We know it facilitates data-driven decision through visual representation. The moment you use visual representation, it's easy to convince any group that you wanted to make a particular decision about. Pattern recognition helps in identifying trends and patterns that are not immediately apparent. So the block of the data is very difficult to get insight into that kind of pattern, but with visual representation in general, you see that it helps you to get immediate and apparent insight. Then the interactive exploration allows users to interact with data and explore various scenarios. So that are the basic benefits that data visualization brings to the general public or to anybody who is interested in the data visualization concept. Okay, move to the next slide. So what are the key components of data visualization or data analytics tools? The key components, one is the data management that you require, which is related much to engineering aspect of the data, efficient storage, retrieval, and processing of large data, visualization techniques, which is actually what we are trying to discuss now, various methods to visually represent data, which were charts, graphs, and maps. And that is actually the focus of my talk, because I have some experience and I am able to develop a particular a chart that is that was accepted to the academic world. Then the interactive interface, which use friendly interfaces that support exploration and manipulation of data. You know, in the analytics, it is more, if you go, for example, those who are working with Power BI and Google Analytics knows this, that it is an interactive phases rather than the coding. So that is about the visual or the component of visual analytics. So this next slide, please. The future trend in visual analytics. In terms of visual analytics, integration with AI is at its initial stage. So enhanced predictive analytics and automated insight generation. I think yesterday I'm trying to generate from AI a box plot, but the image couldn't be generated. So AI is still at a very early stage about the analytics. So this integration process is still an open area. The real-time analytics, immediate processing and visualization of data as it is generated. That is the interactive aspect of the visual analytics. And visual analytics, that is how it is differed a little with the exploratory, where it's not real time most of the time when we are discussing things on exploratory. I'm going to discuss that later. Then augmented reality, combining AR with visual analytics to immediate immersive data. So these are some of the future trends that are going to happen. So next slide, please. So exploratory data analysis. Next slide. The exploratory data analysis, I think this is not the next slide. Next slide. Next slide. Good. The exploratory data analysis, actually, which is the focus of my discussion, and it has some relation with visual analytics. And actually, exploratory data analysis involves summarizing the main characteristics of data using visual methods. And therefore, some of the tools used in visual analytics are first being developed in terms of the field of exploratory analysis, which is my core area of research. I did my PhD in this field. And the purpose of this field or exploratory data identify pattern, support anomalies, test hypotheses, check assumptions. And the technique utilizes statistical graphics, plots, and the information visualization. So if you look at some of this description, you see that both exploratory data analysis and visual analytics have so many things common. So that is why I discuss the next slide. Sorry. So if you go to the next slide, relation between EDA and visual analytics. They shared both aim to uncover patterns, insight, and anomalies in data. The techniques, EDA focus on statistical plots, while visual analytics incorporate interactive visualization. So you see in the visual analytics, it's very interactive, and it's not like a fixed things that we see in the EDA. So this is a clear difference between the two. Data handling, EDA often deals with preliminary data analysis, whereas visual analytics integrate more complex data set and models. So because of that difference in principle, EDA is meant for just simple things. You know, in EDA, we don't combine things, multiple plots at a time. So we just develop a plot from the data and make the analysis. So in the visual analytics, it is far, far beyond that, and it incorporates a lot of characteristics to explore the data. But all in all, the two fields have a very close relationship. So let's look at also the application of EDA and visual analytics. First, in the next slide, if you move to the next slide, first is business intelligence, which helps in decision making by identifying trends and patterns. In healthcare, used to patient data analysis and predicting data disease outbreak. Then in scientific research, aids in data exploration, and hypothesis testing. So these are some of the areas, but I think it's far beyond this. We just make like a selection. So if we move also, the next slide, we have the key components of visual analysis tools. Okay, sorry, like this slide is not supposed to be here. Move to the next slide, please. Next slide. Yeah, well, so this is our case study. Some of the slides, I've been having so many reasons to have some of the ideal slides. Those are not supposed to be there. I haven't cleaned the slides. Apology, please. So the case study, our case study is to look at how can we be able to develop a visual analytic tool. And we have a case study here, stairbox plus construction. And you must have some inspiration. First, being a curious person that where can I start from? So you must have a certain plot that should inspire you. For example, in this work, in the stairbox plot, we look at a box plot, the classical box plot, which is a very simple plot that you draw, as you can see to the right of my slide. That plot was first introduced by Tukey. So this John Tukey in 1970 popularized this plot, and it became very popular up till today. I think many are still using the plot for so many purposes. One among these to identify outliers and to visualize the symmetry, asymmetry, and so on in the data. So let me rush in the literature. If you look at it, there is Frege contribute a lot in '89. Kimber, Carlin, Schwartman, De Silva, Hubert, Bruford, and also we made a contribution even in the classical box plot. That is the Barbara et al. 2017 is one of my submissions. And most of these contributions are attached to the identification of outlier. So that is not the focus of our discussion. They still look alike. Each of the plots developed by this list of literatures are about the pens, where the pen's position should be. So it's not the focus of our research. If you move to the next slide, you see that some adjustments start to be incorporated in box plot. So someone was inspired, for example, McGill. McGill look at box plot and see whether he can incorporate something. He incorporate what is called a notch. So when he incorporates the notch, the display property of the box plot changes. So you see, this simple incorporation changes the visualization, and he was able to contribute in the literature. And it enables someone to visualize and identify a population difference between maybe a sequence of data sets. So also there is some other contribution like Abu Zaid, who also contributed, and Karmala. So they developed some different plots. So also there is so many other plots in the literature which also changes, which are motivated or mobilized through looking the box plot. For example, the Benjamin proposed a base plot, Haynes and Nelson proposed a violent plot, Kamstra proposed a bin plot, and Barrowman proposed a Rensbrook plot. Some of the plots you can see here to the left are inspired by this. So from this, we are able to develop our curiosity and look at the literature, what contribution has been made, and to see what can we do to make our own contribution. So this is the mindset whoever wants to develop any visual tool. or the data visualization tool should look at. Okay, so from there we started. If we move to the next slide, grabbing things from the literature. If you move to the next slide, move again. Okay. Grab slide. Things like the range of a data set. We define it here. We define what is called the quad bin. And this definition is originally from us, whereby we divide the data into 4 equal sections, and each of the sections we call it a quad bin, because what we are trying to do has a little relation with the bin of histogram. Okay, so we want to divide the data specifically into 4, because that is what the box plot does. It divides the data into 4 equal parts using quartiles. So in this case, we divide the data into 4 using the bin, just like box plot. I'm sorry, not the histogram, but we say quad bin because we want to divide it specifically into 4 equal parts. So that's how we define the quad bin. If you move to the next slide, also we define what is called the outlininess, and outlining has been in the literature. It's a data point. So each data point can have what is called outlininess, and is a measure of how far an observation lies from an estimate of a central point of the data, usually standardized by means of robust scale. For example, the median. So if we use a median, we define outlier as a point, distance of the point from the median. And according to our literature definition, it does not matter if the data point is smaller or larger than the median. However, when the distribution is skewed, a scale on each side of the median is proposed, such as adjusted outlininess. So there is in the literature adjusted outlininess, and is defined in the equation 2, where W, L, and W are lower and the upper whisker of the adjusted box plot. So this outlininess also we use to customize another definition. If we move to the next slide, No, back. Okay, back. So we have a definition 2.4 there. Definition 2.4 states that is the stair box plot outlininess. We want to use outlininess to incorporate in our construction. So we define outlininess as SO I of xi, of a data point xi, is a distance between our observation xi and the median. So we are very specific about our central measurement here. So from the median of the data set, x scaled with the distance between corresponding fence cut of value. So mj. So we scale this distance by dividing with difference between the median and the fence mark of value mj's. So depending if it is the lower or upper. So that is why the definition of SOI is in a split form in equation 3. Then we also have another definition. That is definition 2.3. Are you actually in that slide? I think it's the next immediate slide. Can you move? This is where I'm at. Definition 2.5. The scale stair box outlininess also is given by SO alpha, which is alpha SOI, where alpha is a value between 0 and 1. So for the display purpose, we want to have a scale that can compress the value of each individual outlininess of the data point. So I will explain why do we need that in the next slide. So move to the next slide. This a description of what exactly outlininess can look. So if you observe a data point x1 to the left is chosen and lies below the lower whisker fence as outlier, whose value is less than the median. So if their box plot outlininess will be estimated as SO equal to the distance C1 in the image of over the distance D1, also for an arbitrary point XU. So also for the arbitrary point XU from the sample X, so meaning if you look at the plot, there is another point XU. The other one is not X1, it's XL, meaning the lower point, XU, the upper point, something like that. So whose value is more than the median and below the upper whisker. So it arbitrarily represents a point which is not outlier and above the median. So its their box plot outlininess will be given as CU, which is the distance from the median to that point, over DU, which is the distance from the median to the fence. So in general, if the value CI is greater than DI for an arbitrary sample point XI, then XOI will assume a value greater than 1. And thus, such sample point becomes a suspected outlier. So alternatively, so one of the functionality of box plot is to identify outlier. So through this outlininess, outliers can be spotted by these characteristics. So if outlininess is greater than 1, then definitely that point is an outlier. So alternatively, when CI is less than DI for a sample point XI, such point will assume the value of outlininess greater than 0 and is marked as regular or sample point. I think this is an error. It's supposed to be less than 1. SOI will be less than 1, and the sample observation become a regular observation. So it's not an outlier per se. So if you move to the next slide, can you move to the next slide? Okay, thank you. So this is the square box plot outline. This is how we construct it. The first you see, but to the left is the regular box plot, and to the right is our proposed stair box plot. And how the stair box plot was constructed is first the boxes are 4, using what we call the quad bin. So we have 4 boxes containing data points, and the data points were constructed as a vertical line whose width is the outlininess. So square box plot outline was great because it was scaled with alpha to have a better visualization. So we have that. Then in each where the point coincide with the quartiles, for example, Q1, we extend the line to be to the same width with the width of the quad bin at that particular point. So you can see in the second quad bin, if you look at that plot, we see we have the lower quartile, we have the median, while the upper quartile falls in the third quad bin. This particular point. So that point specifically show those points that are at the quartile position, and it also maintain the display of the box plot in that particular sense. And you see also they display each other. So the visual comparison of the regular box plot method to the left against the proposed stair box plot is now in restricted or visualized there. So specifically, we are able to have a plot that can tell us the outlying point, just like what the box plot does. So you can see an outlier point in the above and below as red lines, while regular points below the median are drawn as blue lines. Regular points above the median are drawn as black points. So all this visualization you can customize based on your choice of colors and what have you. So the most important here is you can see the density of the observation is being displayed, and at each quadrille level, how those points differ. So these are some of the information that the box plot could not tell you. And if you move to the next slide, good, you can see the striking difference between the box plot and the regular box plot and the stair box plot, where we visualize simulated data from normal distribution and uniform distribution. And if you visualize this box plot, the shape of the distribution look very, very similar from the regular box plot, because the box plot doesn't capture the density of observation in terms of the shape. So you can just see a symmetric data displayed as normal, also another symmetric data displayed as uniform. You cannot easily distinguish the two. But in the stair box plot case, you can see that the quadribins from the normal data, which is symmetric, the lower quadribin, that is quadribin 1, and the upper quadribin have the same width, while the middle quadribins, which is the second quadribin and third quadribin, has also the same width. So we can see the symmetry in the middle and the symmetry at the tails being displayed in clear terms. But for the uniform, you can see all the quadribins has almost the same width, and that showed exactly the behavior of the uniform distribution. So you can easily identify this kind of characteristic from the stair box plot, so which is definitely an enhancement to the plot that existed or that we wanted to tamper with. So that is the actual contribution, and the application of this was explored. If you move to the next slide, okay, good. In this slide, you can see trends of monthly maximum rainfall data for 31 years. Patelin Jaya, Malaysia, is being observed using the stair box plot. You can also as well do this with the classical box plot, but the trend and the features are more striking and more observing some of the points, how the point differs over this period, how the shape, the characteristic differs over the period, is being more strikingly clear using the stair box plot. So that is our belief. And also, at this point, I sometimes bring to the notice of my audience, why do we need a scale adjusted outlininess? One of the challenge, if you come to batch comparison like this, you can see that the outline points sometimes explode. If you look at the stair box plot for 1975, has a line which overlaps with the adjacent plots that is to it. So that is why you need to control the width using that scale, and it's arbitrarily chosen by yourself based on experience when you are plotting the plot. So this is the contribution. I think we also visualize another data, which is precipitation. If you move to the next plot, it's a precipitation data for 46 years. Also, we visualize, if you move to the next plot, we visualize, move to the next plot, we visualize annual maximum river flow discharge as the one core data. So this is some of the analysis, and we make a lot of interpretation about this display, and we make a lot of insight from what we have seen, because some of this visualization are done to deploy some modeling within some distributions. So stair box plot give you much more idea about what kind of distribution can you use to 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 model the data. So actually, this is square box plots, and this is the visual analytic tools I want to share, and that's my experience as far as contribution. So we make so many other contributions in the field of exploratory data analysis as a collaboration, both in box plot and some other plots like histogram, and we are still working in so many fields. One of the most popular contributions that is being made is mostly about the outlier, how to detect outlier, because that subject outlier um, has been very, very popular in the literature. So even currently, we have uh, a work on stream on the changing the fence using the asymmetry in the data. So how can you change the estimate using asymmetry? So that is also a very important uh, things to look at. There are so many other things to look at in terms of box plot or any other plot, but the inspiration is to find what is the science behind that particular plot, how it comes into being, what can you contribute to it. So that is exactly how to develop a visual analytics tool as far as this talk or my experience is concerned. Um, the next slide. The next slide is my conclusion and final thought, because um, I just conclude that we are talking about visual analytics as a bigger picture. So, so what exactly you wanted to contribute in the field, you need to get inspired from the existing tools. So any of the tools that we use to visualize can inspire you to make a contribution, definitely, by developing a curious mindset that what this is intended for, what can I add to it? That is the curiosity. Then to do that, you must consult relevant literatures in terms of that particular tool you wanted to change. So you have to dig into the literature and see what other contribution are made and what can you do make and that your contribution to stand out. Equip self with technical knowledge of coding is very essential, especially when you want to do the visual, um, sorry, the develop a particular tool. You must have some coding knowledge of, for example, me, I use R and Python in most of my work. So I think there is so many other coding and even more interactive tools that you can use to develop your own journey. Actively participate in academic functions such as this kind of talk and workshop seminars, conferences, collaborate and socialize with academic peers, both physically and virtually, to exchange ideas. So actually, these are my specific conclusion for someone who wanted to develop any visual analytic tool for any insight that you wanted to contribute. These are some of the references we consulted. Um, and lastly, I would like, or I'm deeply grateful to the organizers, particularly the Data Science and Predictive Analysis DASCA, for inviting me to speak at their online session. This opportunity is immensely meaningful to my academic career. I would also like to extend special thanks to Dr. Nurul Nisa Khairul Azmi for her unwavering dedication and hard work in making a great team that enables this session possible despite the challenges. Thank you. Terima kasih, Kirana Menden Gar. Ina godiya. Thank you, everyone. So that's my talk. That's my experience. Thank you for listening.
Okay, thank you very much. Okay, Dr. Baba. So we open a question Q&A session to the participant. Okay, if there any question you would like to ask to Dr. Baba, you may post your question on the chat box. Okay. And then meanwhile, I would like to ask about the step plot here. Can you again briefly explain how to interpret this stair box plot?
Okay. Somehow I talk about it around because initially all this, we call this box the quad bin. Unlike the stair box floor, which has line but below the box and line above the go box, we use box to represent that. And that lines in the box plot are representing the data. And you see in the stair box plot, the data, if you look at the second quad bin, because I cannot be able to touch the interface, but from my own screen here, you can see in the second quad bin, you can see the median line, which is extended to the width of the quad bin. Can you see that? So the data points are being displayed based on their outlying distance that we defined earlier. We know in the previous slide, we defined stair box outlyingness, which is a distance of a point from the median. So all these lines that are spreading, becoming wider, is explaining that this point is bigger, is going away from the median, and when it changes color to red, it will become an outlier. This is how to interpret. And another way to interpret is also about the skewness. You see, also the data is heavier to the left and longer to the right. So it has a longer tail at the top because of the way we display it. We cannot say left and right, maybe bottom and top. Let me put it like that. It's heavier in the bottom and it's longer at the top. So you can see that you can see it's right skewed data from the interpretation because the quad bins have demonstrated that. So these are some of the interpretation that you can be able to make from the data. So you can make insight from identify outliers. You can make insight to identify the shape of the distribution. You can also see each of the individual data points, how heavy they are at each quadrille level or at any of the quartile levels, because the quartile levels are also being displayed as a thicker line. You can see them, and they are extended to the width of the quad bin they fall in. So these are some of the interpretations you can make. And mostly insight sometimes depend upon person what exactly you wanted to identify. So that is it. These are some of the particular insights you can make from this plot. I hope I'm clear enough.
Okay, Dr. Baba. The classical box plot is required us to compute the five statistics, the first quartile, the median, first quartile, third quartile, and the minimum and the maximum. That is the traditional box plot. So in the stair box plot, is it the computation is the same?
Yeah. In terms of estimating the outlyingness, we use outlyingness. So instead of pence that is being used in the classical box plot, in this case, we use outlyingness. So outlyingness is little different, though they share the definition with tense. You understand? So let me go back a little to, I think, slide number 20, or okay, slide number 18. Can you go to the slide number 18? Yeah, thank you.
Yeah.
So if you look at the slide number 18, you see this is a classical box plot, right?
Mm-hmm.
Then from the classical box plot, you can extract the outlyingness information using the distance we define. If you have a point, for example, XL to the left of the plot, can you see it? XL is a point which happens to be an outlier point. You get me? So this represents an arbitrary outlier point. And the distance of the point from the median is CL. We call it CL there from the plot. Then the distance of the fence from the median is called DL. Can you see it? Then stair box plot outlyingness defined for this particular point is equal to CL over DL. You get me? CL, if you leave it as CL, it will be very, very wider. But if you scale it down with DL, it becomes more compact. You understand the point, so that it can be seen in the plot. You understand? So that is how outlyingness is defined in terms of our plot. So the box plot use fence. Our definition use outlyingness to define outlier. So if SO is greater than 1, then that point is a suspected outlier. You understand? Mm-hmm. Just like if the point is above the fence, it is a suspected outlier from the classical box plot. So that are some of the difference that emanate from our plot. I hope my explanation is clear enough to get this insight.
Okay. So is there any limitation of using this stair box plot?
Yeah, there is a lot of limitation which is related generally to exploratory data analysis. You know, there is difference between confirmatory and exploratory. So if we say outlier, you cannot conclusively say this is an outlier. You have to go beyond the box plot. So whatever insight you get is not a confirmatory insight. So that is specifically the things that you have to be careful. And sometimes their box plot is more informative than the original or classical box plot. So it might be challenges during interpretation to especially those who are not specialists in the area. So there is so many other limitations that might come as you try to explore the plot. So I think basic limitations is the limitations that are defined when using any exploratory tool. You cannot use them for any confirmatory purpose. That is the basic. So for example, when you are trend analysis, you cannot say this population is different from the other subpopulation by simply seeing that they are not having the same median or they are not having the same quartiles. So you cannot make such kind of deductions from there, but it gives you some ideas about what should you do when you are trying to do the confirmatory aspect of the data analysis. So I think that's my response about the limitations.
Okay. So any question from the participant? Okay. Yeah. Actually, stair box plot is one of the data visualization, which is very good in identify the distribution of or the shape of the distribution of the data. So actually in this case, Dr. Baba use is it extreme value data
Yeah, in
to
our paper,
visualize the
we
step
publish.
box plot for this one? So that
Yeah,
we
this
can
is an extreme data.
yeah.
Yeah, this is an extreme data, annual maximum data. It's an extreme
Mm-hmm.
data. Yeah, it's an extreme data. Yes. So even in the extreme data, you can get a suspected outliers, and you must try to see how you can handle them. Yes. So the annual maximum, most of the data I use during my research are the extreme data because of the mindset of my supervisor, late Dr. Bakri. He's an
Mm-hmm.
expert in the area, and he always gave us advice to use the extreme data. So, so I visualize the extreme data. But beside the extreme data, you can see that we also visualize simulated data set. I think in slide number 20, sorry, slide number 20, this is a simulated data, which is from normal and uniform. And you can see how those the characteristic of the distribution from the plots there. Yes.
Mm. Okay. Um. So basically, if the data is normally distributed, so
Yeah.
does the box plot and stair box plot are equally good, or is it stair box plot works much better compared to the
Yeah.
box plot?
Yeah. Yeah. You see, the box plot, what the display in the regular display or classic box plot we know. So if you look at the display in the light, you can see that only the separate in the middle differs. And the separate does not tell you much about the distribution, isn't it? Look at the two plots, normal and uniform. You understand? The separate of the box doesn't tell you. You can even still have a data from normal that will have the same similar separate with this that of the uniform. So that cannot tell you exactly about the data, but I'm sorry, the distribution. You can
Mm-hmm.
see what you see here is just like having a data which is metric. But when you look at it with stair box plot, you understand, you can see that the middle of the data, you understand, is
Mm-hmm.
heavier
Yeah,
or
yeah.
normal, while for uniform, the separate of the data is almost uniform all along. You understand? You can see the width in the middle, in the first quadribin, second quadribin, third quadribin, and fourth quadribin. Just like displaying it with what? With histogram. So it gives you some insight from histogram and along with the power of the box plot. So that is what the box plot does. So it combines some features of histogram about the distribution, the shape of the distribution. Because histogram give you more information on the shape of distribution than the box plot. So we incorporate that quadribin to reflect some of the power of the histogram, even though we cannot control or we cannot divide it more than the four quadrants or below the number of the, so we are very specific in our definition that the quadrant has to be four so that to maintain some of those characteristics of the box plot. So that is actually uh, some of the powers of the stair box plot over that of the regular box plot.
Yeah, it's very interesting because we can see how the observation itself distribute in the step box plot.
Yeah.
And then
Yeah.
do you have the coding in R package for the step box plot?
Yeah. Actually, we have the base code. So it's still an under development stage. If to say I have a lot of students, we can develop it to have a very powerful package below the basic plotting function. Actually, we have the plotting function, not in form of the package of an R package. So if you simply take the codes on the floating function, run on your run on your system on the R console, then you can generate the data or you can insert the data and then plot. That is what we have so far. So I'm looking for students who can, develop some of those things further.
Because we want to come up with the box plot in our programming, then we just call the function of box plot, then we can just produce the box plot. Yeah, for the stair box plot. So is there any package to come up with this?
Yeah, that's what I said. We have a function. There is no package yet. Okay. It's a function. It's not made as a package. So it's a function, just like the way you can write any R function. You understand? Any R function. So we write a function that will make the plot. So far, this is where we are. We haven't yet developed any package like the base package. Boxflow is very, very popular. So it has been for a while. So any system, you can easily have a plot. Sorry, a function that will do that work for you. But for us here, you need to talk to us if you want to plot. We need to collaborate to share the code with you. Yeah. I have to share with the code with you. It has not been released as a package yet to any of the communities.
Yes, because I think that if we can publish the coding to the R community, then everybody can get benefits from the stair box plot, especially those who are from practitioner, and also provide some comparison. Basically, this is just for one set of data. So if they have what, and then perhaps that will make more useful for the community. Okay. I guess that's all for today. Okay. So thank you very much. But for your excellent presentation today. But before we end this session, can we take a group photograph?
Okay.
Please kindly turn on your cameras to all participants, and then the community will take the picture on the count of 3. Okay?
Yeah.
Okay, committee. Okay, can you start count?
So we have 8 participants, or are we more than that?
Okay, so 1, 2, 3.
Okay.
Okay. And then okay, so actually we have the feedback form, okay, on the chat box. Okay, please fill in the feedback form here, okay, and also so that we can provide the attendance and then put in what we call it as jam latihan. Okay. So thank you very much, okay, to all of the participants, okay, and then before we conclude this sharing session, so I would like to once again extend our heartfelt thanks to Dr. Babura for his insightful presentation, and then we hope to collaborate on research or publish paper together in the future. And then it has been an honor to have you with us today. Thank you to all the audience members for your support and participation. Before that, we also like to have some announcement. Okay, DASCA will organize have some future events. Please committee share the future events. On 17th of August, okay, we have a time series and forecasting workshop, okay, online workshop. So we would like to invite all of you to come to join our workshop. And also on December, we also have another workshop, okay, on predictive modeling series, structural equation modeling, 19 November. Okay, so the SAM courses, SAM course, okay, will help in class, okay, face to face at UiTM Cawangan Negeri Sembilan. So open to only 25 participants. Okay. For time series workshop, okay, it's online session and only open to 60 participants. Okay, it's a 1-day workshop. Okay, so thank you very much to all. Okay, thank you very much, and that's all. Thank you very much. Assalamualaikum.
Thank you.
Thank you very much, Dr. Baba.
Okay, till we communicate. Thank you so much, Dr. Nurul.
Okay, thank you very much.
I would like to see more collaboration between us. Well,
Sure,
last we collaborate,
definitely.
I think it's since at UVM. Thank you for giving me this opportunity. Thank you.
Okay, welcome.
I'm going. Bye.